So far, we can do addition of functions, the product of functions, and work with polynomials. But what about composite functions? Well, a composite function is a function of a function that we would say f of g of x, where we would take x and c, where g of x maps that to, and then c where the output g of x is mapped to using the function f of x. A good example that is applicable to derivatives is what is the rate of change of a snail traveling 4 meters per hour in meters per second? Well, to express the position of the snail using the variable s in regards to time in hours, where hours is represented with an h, we get s of h equals 4h. So we have our outer function being s of h, as we saw with the function f in f of g of x. Example. The inner function now is h of t, where t is the time in seconds. And since there are 3,600 seconds in an hour, we express h of t as h of t equals t divided by 3,600. Now, altogether, the snail's position in seconds is the function s of h of t equals 4 times t divided by 3,600. Remember, the function s isn't the position of the snail, but rather the function that takes a time in hours and gives the position in meters. So now we can look at the rate of change, where here we are looking at ds of h of t by dt. If we simplified our expression, we'd get s of h of t equals t divided by 900. So the snail is traveling 1/900th of a meter per second. But what if we couldn't simplify it? Well, we know that the snail is traveling at 4 meters per hour, being the rate of change of the outer function. And if we multiply that by the conversion rate, 1 hour per 3,600 seconds, we'd get our answer of 1 meter per 900 seconds. And how do we get this conversion factor? Well, it's the rate of change of the internal function. In general, we write this as d by dx of f of g of x equals g prime of x times f prime of g of x. We shouldn't be mixing notations usually, but I think this most clearly states that the derivative of a composite function is the derivative of the inside function multiplied by the derivative of the outside function in terms of the inside function. In purely Leibniz notation, it looks like the dg terms cancel out. We're going to look at the fractions here. df by dx equals dg by dx times df by dg. dg on top and dg on the bottom cancel out, it looks. This isn't technically rigorous, but it will help you remember. It's worth noting that in Leibniz notation, dg and df are infinitesimal changes in the functions, just like how delta f and delta g are the change in f and g respectively without being infinitesimally small. Now, there's a whole lot of problems with df and dg, and they actually ended up being resolved in the 20th century, but I'm not going to get into that. To prove such an assertion, let's rename the composite function by saying f of g of x equals q of x. We also need a different definition for our derivative. So instead of f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h, we will rename x plus h to the point a, and just move a infinitely close to the point x, so it will now be f prime of x equals the limit as a approaches x of f of a minus f of x all divided by a minus x. And this does indeed preserve the whole slope formula idea too, if you want to look at it that way. So let's write out what q prime of x is first. Q prime of x equals the limit as a approaches x of q of a minus q of x divided by a minus x. Now, if we go back to f of g of x, it is the limit as a approaches x of f of g of a minus f of g of x all divided by a minus x. Let's roll with the idea of fraction canceling out thing and multiply dg, the infinitesimal difference in g being defined as the limit as a approaches x of g of a minus g of x onto the top and bottom. Now our derivative, after we swap numerators to make it not redundant, is the limit as a approaches x of g of a minus g of x divided by a minus x times f of g of a minus f of g of x all divided by g of a minus g of x. Clearly, on the left, that is the definition of the derivative of g of x. But on the right, things are only slightly more complicated. With some more renaming, this time, the outputs g and a and g of x to a and x. This would look like the derivative for f prime of x. And now just replace the capital X with g of x, and we arrive that the limit that was on the right evaluates to f prime of g of x. All in all, proving the formula that d by dx of f of g of x equals g prime of x times f prime of g of x. For a brief example, and I will go through more examples in a future episode, let's look at f of x equals x squared plus 3 all cubed. Our inner function in this case is x squared plus 3, and the outer function is u cubed. Not to be confused by the fact I used a u for the outer function, mind you. It's just a placeholder for an input variable. So the derivative of an inner function is 2x, and the derivative of the outer function is 3u squared. Altogether, f prime of x equals 2x, the inner derivative, times 3x squared plus 3 all squared. Simply replacing the placeholder u with the inner function. Now simplifying things, we say that the derivative is f prime of x equals 6x times x squared plus 3. You're welcome to try this yourself by multiplying everything out as well. Well, that's a wrap for this episode, unfortunately. But there's a lot more material on its way. The next video will be the quotient rule, followed by trig derivatives. And then there will be more examples of derivatives for additional practice. And as always, keep on learning.